So section 1.4, continuity and one-sided limits. So let's first look at continuity at a point and on an open interval. So at a point just means, hey, here's a function. Is this function continuous at this point? And open interval means we have an open interval of x values, and is this function continuous everywhere along that open interval? So continuous, it means much the same as you would think. There's no interruption, there's no break. If it's at a point, that means that there is no break at that point. The function just goes seamlessly through that point as you would expect. If it's over an open interval, there are no breaks, and it says it here, no holes, jumps, or gaps, okay, at a point or over the entire interval. So here we have three types of or examples of functions that are not continuous at a certain point. So this first function here, it says f of c is not defined. So there's a value c such that the function is not defined. It's defined everywhere else. So this is not continuous because, and one of the ways we describe this is a function is continuous if you can go from one side and draw to the other without lifting your pen or pencil off of the paper. So because of this hole, we know this is not continuous. Okay, we call that a hole. Now this one has a jump, and the limit, notice that limit does not exist because we're approaching two different values from each side. Now, in the first one, that limit does exist, but the function is undefined at the point C. This one, the limit exists, but the limit as x approaches c of f of x does not equal f of c. So these are three conditions for which the graph is not continuous at x equals c. So if the limit doesn't exist, if it's undefined, or if the limit doesn't equal the value. And we're going to use those in our formal definition. So here's our definition of continuity at a point. And we're going to use those three types of discontinuities that we saw on the last page to give us the conditions of when it is continuous at C. So f of C is defined. Now, all three of these conditions have to be met. So f of C is defined, and the limit as x approaches c of the function exists, and they equal each other. So the three things required for continuity at a point are these three things: that the function is defined at when x equals c, that the limit exists as x approaches c, and that these first and second ones equal each other. Now, so that's just at a point. Now, on an open interval, we say that it's continuous on an open interval from a to b. So that's like saying we have the x-axis, here's a, here's b, here's our function, if it's continuous at each point in the interval. And a function that is continuous on the entire real number line is everywhere continuous. Now, most often, there are only, for most functions, there are only a few points that are not continuous, and so generally we can come up with intervals, and sometimes very large intervals, that the function is continuous over. Now, let's talk about a few things about discontinuity. Okay, so consider an open interval I. Now I'm going to read this, you could read this on your own, but as well, part of this is how a college math textbook would read. This is what we're talking about, and we need to be able to become more familiar with these so we can understand what we will see in future math courses. So consider an open interval I. So we're just assigning a letter I to some generic open interval. Really doesn't matter, we're just considering some open interval I that contains a real number C. So I have no idea what it is, we're being very generic. So here's our interval I, and here is some real number C. If a function f is defined on I, except possibly at C, and f is not continuous at C, then f is said to have a discontinuity at C. So if we have a function that goes like this, except it's not defined here at C, so let's erase part of that right there. We can put a hole there. Then we say it has a discontinuity at C. Now, one of the reasons they have the first part of that definition is because if we're looking at the square root function, or a square root graph or something that looks like it, and our C's over here, well, the function is not defined on this interval at all. So we would not say it has a discontinuity there. But if this was our C and we had a discontinuity up there, because there's an interval around it that it is defined, except for maybe at C, we would state that there is a discontinuity there. So not here where it's not defined, because it doesn't even make sense to say it has a discontinuity. Here where it's generally defined, we would maybe expect to see that, but no, there's a discontinuity. So there's two main categories of discontinuities: removable and non-removable. And I like these graphs to depict these. So a removable discontinuity is if, in the AP Classroom videos say, if you can plug the hole. If you can put in one point and now the function is continuous in that interval, it's a removable discontinuity. If you cannot just plug the hole because there's a big gap or something, then it's a non-removable discontinuity. Now, please note, even if the function is defined at C, this is a discontinuity because it doesn't equal the limit. We would still call this a removable discontinuity because if we can just plug that hole and put that point in there, the function becomes continuous and it is a removable discontinuity. So, example 1, discuss the continuity of these functions. So, let's take a look. Now, one of the things that is helpful to discuss continuity, generally speaking, especially as we begin, is looking at the graphs. So if we look at the graphs of these, we might be able to see, obviously, if there are any discontinuities or where the function is continuous. One of the things that we will need to develop is to be able to look at a function, in particular a rational function, and describe the discontinuities that we see. So here we do have a rational function. I know that this function is going to be undefined when x equals 0. Okay, x cannot equal 0, this function. And we could sketch a quick graph here. So as x approaches 0 from the right, it's going to get bigger and bigger. As x approaches 0 from the left, it's going to get smaller and smaller. It's going to approach negative infinity as it goes to the left, positive infinity as it goes to the right. So that limit doesn't exist. We're discussing the continuity. So this would be continuous from negative infinity to 0 and 0 to infinity, and it has a non-removable discontinuity when x equals 0. So that's how we describe the continuity. We want to give the intervals where it is continuous, or perhaps state where it has discontinuities and say that it's continuous everywhere else. Now again, in a square root function, stating the continuity is related to the domain, so we may want to state that explicitly in that case. All right, on this one, x squared minus 1 over x minus 1, I know that x cannot equal 1. So again, that denominator cannot be 0. So we have 1 minus 1 is 0. There's going to be a discontinuity there. Um, if we were to graph this, we would actually see something that looks a lot like this, except there is a hole there when x equals 1. So again, I'm going to, instead of stating when it's continuous, I'm going to say there is a removable discontinuity at x equals 1. So again, this time it's removable because if I can plug the hole and then make it continuous, that's a removable discontinuity at x equals 1, and continuous everywhere else on the real number line. So now let's take a look at C. This is a piecewise function. That means that this function follows different rules for different parts of its domain. So x plus 1, when x is less than or equal to 0, that means it's going to be looking like this. So it's just that line x plus 1 to the left and including the y-axis. And e to the x when x is greater than 0. Well, e to the 0 equals 1, so it's going to go like this, and then it grows like so. Now, if I were to look, if the question is this continuous at this point? I know this line to the left will be continuous, or the function to the left that follows that line will be continuous, and the e to the x is continuous everywhere. So is it continuous? Well, what is the limit as we approach 0 from the left? It's going to be approaching 1, and the limit as we approach it from the right is also 1, and the function equals 1 at that point because we have this less than or equal to, and we know that function equals 1 when x equals 0. So this seems to be continuous everywhere, or continuous from negative infinity to infinity. All right, y equals sine of x. We are familiar with the sine function. Know that it just cycles back and forth and back and forth. And again, this is continuous from negative infinity to infinity. Now, what we're going to move to is now looking at continuity on a closed interval. Okay, so we've been looking at continuity on an open interval, which means parentheses, meaning we're not actually looking at the endpoint of this domain. What we want to do is move to a closed interval where we are looking at the endpoint of that domain. Notice on these graphs, here you have open circles, meaning we're not actually looking at the value of b. We need to look at we need to figure out how we can look at the closed interval. And to do that, we have to look at the one-sided limits. Now, we've already talked a little bit about this, and I've used it, and it's pretty intuitive from what we've discussed. And so this is the limit from the right, or right-handed limit. And that's where we have the C plus. Plus means from the right. So if you were thinking of this visually on a graph, if you're looking at a right-handed limit of a function, you are coming from the right, so you're actually moving left if we were looking at this value C. So positive means from the right or the more positive side. We actually are moving left. That's a little bit unexpected there, but that's what it means, limit from the right. And it'll be similar on the other side, coming from the left will be actually moving right if you're thinking about that visually, approaching that. So here's our limit from the left, or left-hand limit. Again, we've got that C minus. And again, you'll be approaching from the left, which means you're moving to the right if you visualize traveling along that function. Now, one-sided limits are useful in taking limits of functions involving radicals if you have an even index, if n is an even index. Okay, because if we have the square root of 0, There is no limit from the left because the function doesn't exist. So we'll just take a one-sided limit, and we'll go take that limit from the right. So let's look at example 2, a one-sided limit. Find the limit of f of x equals the square root of 4 minus x squared as x approaches negative 2 from the right. So if we were to graph this, we would see that this is actually a semicircle with the center about the origin and a radius of 2. So we're going to approach negative 2 from the right. We can look at this graphically now and see that we're coming down here closer and closer to 0. So the limit, I'm going to use my notation, the limit of our function f of x as x approaches negative 2 from the right, so we're going to have our plus sign, equals 0. Now, if we were wanting to do that without looking at the graph, we would probably be putting in and seeing what these values are. Now, again, to find a limit, analytically, the first thing I would suggest doing, the first thing we talked about in the last unit, was plug it in. So this would equal the square root of 4 minus 4, which is the square root of 0, which is just 0. So analytically, that just substitute that value in, and that gives it to us. Because the square root does equal that initial position, okay? Now, we can also use it to investigate the behavior of step functions. Step functions are not often used. You might use them, those who go on to study mathematics in college might see them more, so this is just a brief introduction. And this is the greatest integer function. And essentially, kind of what it means is you round down. So this notation is the greatest integer n such that n is less than or equal to x. So the greatest integer of 2.5 is 2. And the greatest integer of negative 2.5 is negative 3. And this is what the graph looks like. So if you're here at 2.5, that has a value of 2. The input is 2.5, the output's 2. If you're here and the endpoint's negative 0.5, well, the output of your function is negative 1. So find the limit of the greatest integer function, f of x equals the greatest integer of x, as x approaches 0 from the left and from the right. So these are two separate one-sided limits. Now note that the general overall limit of f of x as x approaches 0 does not exist, okay, because they will be approaching different values. But we can find the one-sided limits without a problem. So the limit as x approaches 0 from the left, limit of f of x as x approaches 0 from the left, will be negative 1. And the limit of f of x as x approaches 0 from the right will be 0. So those are the one-sided limits for the greatest integer function. All right, so now we have theorem 1.10, the existence of a limit. So the limit of f of x as x approaches c is L if and only if the left side and the right-sided limit match and they meet each other. So this is another way to have that formal definition. So the limits have to match as you go from the left and to the right. So now that we've got that idea of the one-sided limit, now we kind of redefined a limit using these one-sided limits. We can also define continuity on a closed interval. So a function f is continuous on a closed interval from a to b when f is continuous on the open interval. So we apply the definition for the open interval, and that the limit as x approaches that left boundary from the right side equals f of a, and the limit as x approaches the right boundary b from the left equals f of b. So essentially it just means it goes to the points and the endpoints are what you would expect. It's what those limits indicate they should be. So if you have a function that looks like this, and we're looking on this interval, we have a point here, but this has a point here, this function is not continuous on the closed interval. The left boundary matches, again, so that limit, let me switch colors, that limit here goes to the value of the function, but the limit here does not go to the value of that function. So this would not be continuous on the closed interval. It would be continuous on the open interval, but not on the closed. This one we see does work, and this is continuous on the closed interval. So now, example 4, let's discuss the continuity of f of x equals the square root of 1 minus x squared. So again, when we see this, I see a semicircle, but we can discuss this. The domain will be, just to make that match, domain will be from -1 to 1 on the closed interval. Okay, outside of that, this function does not exist in the real number system. And so, is this continuous on the closed interval? That's our ultimate question we're looking at right now. So, it would be continuous on the open interval, and the limit as f of x approaches -1 from the right we need to figure out what that is and make sure that it equals f of -1. So to do that, let's just take a look at the graph. Here's -1, +1, and this goes up to 1. So the limit does approach 0, which is in fact what f of -1 also equals, is 0. And then we need to check the right boundary point, limit as x approaches 1 from the left of f of x equals 0, which is also what f of 1 equals. So this is continuous on the closed interval, continuous on the interval -1 to 1. Now, because I put brackets, it is the closed interval from -1 to 1. Now we have properties of continuity. Okay, so remember we had properties of limits, where if we do certain things to functions, we can still figure out what their limits are without having to calculate the new function. Similar thing with properties of continuity. If b is a real number and f and g are continuous at x equals c, then the functions below are also continuous. Okay, so what we're looking at is these types of operations do not change whether a function is continuous or not. A scalar multiple, okay? If you add or subtract two continuous functions, if you multiply continuous functions, if you divide continuous functions, provided that g of c does not equal 0. All of these things, okay, multiplying by a number, adding or subtracting, multiplying or dividing, provided the denominator is not 0, will maintain continuity. Now, when we discuss continuity, most functions we deal with are continuous at every point. And so we're just going to list those out. As we talk about continuity and discontinuities, we're going to focus in on ones that are not continuous at every point. But it's good at this point to just say, hey, if you have a polynomial, it is going to be continuous everywhere. Okay? A rational function, r of x equals p of x over q of x, will be continuous every point as long as q of x does not equal 0. So we're going to hone in on this when we talk more about discontinuities, when that denominator does equal 0. A radical will be continuous on their domain, and it does state that up in the sentence. Trig functions, sine, cosine, tangent, cotangent, secant, cosecant. Again, they're continuous at every point on their domain. Now, we have to be careful because we know that tangent has asymptotes. So this point right here, pi halves, is not in its domain. So there is a non-removable discontinuity at pi halves and negative pi halves. And it's periodic, so we see that continuing on. But on its domain, it is continuous. We also have exponential and logarithmic, so a to the x or e to the x and the natural log of x, all of those are continuous on their domain. So let's take a look at these new functions and apply the properties of continuity. So here we have two distinct continuous functions and we are adding them together. So by our properties on the previous page, if you add functions, I think that was the second one, the resultant function is continuous. So f of x is still continuous. Tangent, now I'm saying continuous on their domain. It may not be across the entire real number line. So 3 times tangent of x is continuous on its domain. Okay, so if we multiply by 3, it will still be continuous on its domain. Well, that doesn't change it. Now, x squared plus 1 over cosine of x. We have two distinct functions that are being divided. So this is continuous on its domain. Cosine of x is continuous on its domain. When we combine these, we have cosine of x in the denominator. This will sometimes equal 0. So the domain of this function is now different because the denominator has to not equal 0. However, we can just say that this function is continuous across its new domain, making sure that denominator doesn't equal 0. Okay. Now, continuity of a composite function. If g is continuous at c and f is continuous at g of c, then the composite function given by f of g of x, or f of g of x written this way, this just is utilizing the two different notations that some books use, just so you can see them both, is continuous at c. Okay, so let's look at what that means. Here we've got c, and this is g of x. So this gives us some, we'll call this b. So b is the output of g of x. And then we've got some other function, do that in a different color. And this is b, so this is the function f of x. And it's continuous at f of b. That means it's continuous. So notice, just to match the notation, b equal g of c, so I just substituted b into that function. Here, they just give it, so being evaluated, this function that's being continuous here at f of b. Okay, now, example 7, testing for continuity. This just means we're describing the intervals on which each function is continuous. So, tangent of x. We discussed and drew that above. So let's try to describe the intervals on which it is continuous. Now, tangent of x has values that are undefined. Let's see, when x equals pi halves plus pi or 2 pi or negative pi, so we call that n pi, where n is an integer. Okay, n is an element of the integers. So that means it's continuous from negative pi halves to pi halves. Those are open intervals, okay, because we know it will not be on a closed interval. And from pi halves to 3 pi halves, and 3 pi halves to 5 pi halves, and it will keep going that direction, and we could keep going this direction from negative 3 pi halves to negative pi halves, and keep going that way. So those are the intervals over which it is continuous. Now the book says maybe we could shorten that up and just say that the tangent function is continuous on the open intervals in its domain. Okay, not closed intervals, but the open intervals. So if we look at g of x equals sine of 1 over x when x is not 0, and 0 when x is 0, let's see what happens here. Now, we looked at the graph of sine over 1 of x before, and if you remember, that's the one that came up and then went back and forth a lot real quick and then came out. So this is oscillating behavior. Let's draw the axes there. And the limit does not exist of sine of 1 over x. And so this is not going to be continuous at x equals 0. Because remember, for a function to be continuous at a point, f of c has to be defined. So in this case, sorry, that's based off of our notes. G of 0 needs to be defined, and it is. And the limit as x approaches 0 of g of x has to exist, which it does not. Does not exist. And then these two have to be the same. So because the limit of sine of 1 over x does not exist, this is not continuous at x equals 0. So this would be continuous from negative infinity to 0 open interval and 0 to infinity. Now for this last one, h of x, I'm going to show you this graph here. This comes from the book because it's similar to the second one, except we have this factor of x, and that changes it totally. And as we see here, we can set two functions, y equals absolute value of x and y equals negative absolute value of x, and we can use the squeeze theorem to say that the limit does exist. So now because this limit exists and that limit is 0, we don't have the problem with the previous one, and so this is continuous everywhere. Now, theorem 1.13, the intermediate value theorem. So let's read this and try to make sense of this. The words here, and then I'll draw a graph, and it will make more sense if you struggle to understand. If f is continuous on the closed interval, a to b, and f of a does not equal f of b, and k is any number between f of a and f of b, then there is at least one number c in AB such that f of c equals k. So let's take a look at what that means, and let's just draw a sample function. And we're going to start with the things we know. So f is continuous on the closed interval a to b. So I've got a and b here. Now, f of a does not equal b, f of b. So sometimes we forget these are just the y values associated with it. So let's say here is f of a. That means we have a point right there. And here is f of b. That means we have a point right there. Now k is any number between these two y values. So let's choose k to be right here. Then there is at least one number c in the interval. So that means there needs to be some number c here. Now it might appear anywhere. We don't know where it is, but we know that it exists somewhere such that c is paired with k. Now let me just draw a few examples. And essentially what this means is you cannot draw a continuous function from f of a to f of b without passing through all of these points here. Okay, now maybe it comes here and then goes down, but you pass through k. Maybe it drops real quick. Maybe you go through it multiple times. We can't tell that information from this theorem. This theorem is what we call an existence theorem. Now that's in the remark here. This is just saying that it exists. Sometimes that gives us very valuable information, and other times it is not that important to know, or it doesn't help us that much. Okay, but the intermediate value theorem, this is something that we will use throughout the course. Now, one valuable or beneficial use of the intermediate value theorem is to find zeros of polynomials. Okay, so use the intermediate value theorem to show that the polynomial function has a zero in the interval 0 to 1. Okay, so we have our interval from 0 to 1. So I'm going to find f of 0, that's negative 1, and f of 1 is 2. So because, and we're going to go through the intermediate value theorem stating its conditions so that we can draw the conclusion and say that here is our value. So we have a continuous interval because all polynomials are continuous everywhere. And f of a does not equal f of b because we have negative 1 and a positive 2. Now there is some value k in between those, so that's our 0. Our k is 0 because 0 is between negative 1 and 2. So that by the intermediate value theorem, there has to be some value c in here that the function passes through that value 0, or in this case, the x-axis. And that is using the intermediate value theorem to show that this polynomial has a 0 in this interval. And that is our section on continuity, one-sided limits. Remember, we found continuity of open intervals and closed intervals. We talked about discontinuities, removable discontinuities, and non-removable. Thank you for watching.